In this talk, I will discuss our work in defining a semantic model for the RxJS library. I will briefly explain our motivation for this work, and then I will elaborate the motivation with a simple example. After that, I will talk in detail about the structure of the operational semantics for RxJS. I will discuss a few ideas of how to use the semantics for debugging purposes. Finally, I will briefly talk about how we have implemented a subset of RxJS by following the semantics. RxJS is a JavaScript version of reactive extension, which is a push-based reactive programming library. RxJS is often used in web projects to implement asynchronous data flow logic, along with frameworks such as React or Angular. Debugging RxJS program can be challenging. The cause of error may not be revealed with traditional debuggers using breakpoints or by printing out the stack trace, which do not correspond to the data flow of the program. A lot of the details from the library can complicate inspection. Subscription to the observables may be stateful, which is also not well documented. I will use a very small example to illustrate debugging challenges. In the example, a RxJS program reads a content string in a text box for every keystroke, and then sends it for remote query. When the query returns, the result is displayed. So this represents a grossly simplified type-ahead application. If a new query is sent before the previous query completes, then the old query result is ignored. This is implemented using a switch map operator. If a user types multiple characters quickly, then the query takes a while, then only the last query response is displayed. Problem with this code is that some queries may result in errors, but it could be due to the user hasn't finished typing the correct query yet. So we would like to ignore the errors. However, any error in RxJS will propagate outwards until it is either caught or causes the program to terminate. In this case, if there's an error event due to query, the entire program will stop when the error is handled by the top-level subscriber. An initial fix to this problem is to add a catch error observable to catch the error event before it propagates to the root subscriber, which would terminate the program. However, in this case, it is too late. The catch error call happens after the switch map, which would terminate the switch map when it catches the error. The switch map observable source is the from event observable. When the switch map is stopped, the program will no longer respond to typing in the text box. This relationship is more obvious from the diagram, where the catch error operator guards the switch map instead of the from observable. Catch error always terminates its source observable if an error is received. In this case, it terminates the switch map, which is the whole program. Fixing this is quite easy. We just need to move the catch error operator inside the switch map to guard the from observable directly. With this change, the error event will only cause the from observable to be terminated, while the switch map observable still operates. Also, this fact is much clearer from the diagram, where we can see that the catch error operator guards the from observable. This type of error may be due to the misunderstanding of the catch error semantics, that it terminates the source observable it is guarding. Consequently, an error from a component observable can cause the containing observable to be terminated. RxJS has over 100 operators, which based on purpose may be grouped as combination, condition, creation, error handling, multicasting, filtering, transformation, and utility. Each operator creates a different observable, and the subscription to these observables may be stateful. When an error occurs, user may face a challenge of determining the order of execution and the occurrences of events. Clarifying the meaning of common operators may be useful to this cause. Also, a semantic model may be useful in developing a debugging platform for this type of programs. Represent the runtime state of RxJS program using a heap and a queue. The heap maps variables to shared observables and references to subscription objects. The queue stores events and their targets. The events may be internal or external, where the internal events go to the front of the queue so that they can be handled immediately, while the external events go to the end of the queue so that they will be handled in turn. This is consistent with the default scheduler of RxJS, which relies on JavaScript event loop for handling external events. An event may be the next event with a value, and an end event that signals the completion of the observable and an error. We use a variable O to denote observable values. We picked a few representative operators from the major group of RxJS operators. The choice to include enough complexity so that the model may be extrapolated to other operators without major extensions. We included a number of observables. For example, the from event observable emits event from a DOM element. Combine observable combines the latest values from each of its source observable. Concat runs two source observables consecutively and emits their events. Every emits true if all events from the source observables satisfy the predicate function f. Catch error handles error. Take observable returns the first n element of the source. Map observable transforms the event value using a function f. Switch map maps the event value of the source observable to the function f and then joins the resulting sequence of observables. For simplicity, we only consider expressions such as observable values, subscribe, unsubscribe operations, assignment of shared observable, sequence, function, and function calls. Subscribe operation may be at the top level with a continuation function to consume the output event for side effects. Internal subscribe operation is a runtime entity that will be reduced to a subscription object in the heap. There are four types of reduction rules. The first type of reduction rules models the evaluation of expressions, which is the synchronous part of the computation. The second type models the subscribe operation that reduces to a subscription object while resulting in a new heap. The third type models the unsubscribe operation that leads to a possible new heap. The last type models reaction to the internal or external events, which may result in a new heap and a queue. Computation of RxJS program consists of three phases. The construction phase evaluates synchronous code, executes subscribe and unsubscribe operations. Then it enters the reactive phase so that it can respond to internal or external events. And the reactive phase may transition to the sequential phase again to evaluate more synchronous code. after which you go back to the reactive phase to wait for more events. The subscribe operation recursively subscribes to each component observable and constructs the data flow graph. For example, if the combined observable is subscribed, then its two source observables are subscribed, and the references to these resulting subscription are saved in the subscription to the combined observable. The subscription object also includes the last emitted values from the source observables and the number of completed sources, which is needed to determine when to terminate. When a switch map observable is subscribed, its source observable O prime is also subscribed. The resulting subscription object contains reference to the subscription to O prime, while there's no child observable initially. It also contains a Boolean flag to indicate whether the source or the child observable has terminated. RxJS has several forms of shared observables, which are called subjects. A shared observable can have multiple subscribers, while other types of observable have just one subscriber. The share operator returns a shared observable that controls the lifetime of the source observable using reference counting. That is, when the shared observable is subscribed the first time, its source observable is also subscribed, and its events are broadcast to all the subscribers. Subsequent subscription to the shared observable will reuse the subscription to the same source. Other forms of shared observables allow users to explicitly control when the source observable should be subscribed to, which we did not model. Now we have seen a few rules for constructing the data flow graph. Let's look at a few rules that handle event propagations. These rules concern the transition of states that include a heap and a queue, which holds immediate events that are waiting to be processed. The simplest rule is for from event observable, which emits an external event, and it is placed at the back of the queue for processing. RxJS uses JavaScript event queue to handle external events. This model is consistent with the behavior where external events are processed in the order in which they were received. The rules for combined observable are a bit more complex. The observable is also called combined latest in RxJS, where each of the source observable needs to emit at least one event values. So our first rule for combine says that if one of the source observable has not emitted, while the other source observable does, then nothing will be emitted. Note that the rule matches the recipient of the event on the top of the queue with the source observable of the combined observable. In implementation, this is handled by callbacks or promises. The second rule for the combined observable applies when both sources have emitted values, and when one of them emits again, the combined observable emits the value of the sources as a pair. Note that the emitted value is an internal event, which is placed in the front of the event queue. This makes sure that the internal events are processed ahead of the external events. This semantics is consistent with the default scheduler of RxJS. We can also support a synchronous scheduler by putting all the internal events at the back of the queue. The catch error observable monitors error events from its source. If an error event is received, the catch error observable runs its error handler function, which returns a new observable. The subscription to the new observable replaces the catch error one. After that, it unsubscribes its source observable. Like the combined observable, the switch map also needs multiple rules to describe its semantics. Recall that switch map has a source observable R1, and also may have a child observable R2. When the child observable R2 emits an event, the switch map observable simply re-emits the event value as an internal event. The second rule concerns the case when the source observable of the switch map emits the first time. The observable returned from the function f is subscribed to and becomes the first child observable of the switch map. The third rule is similar to the previous one, but in this case, the source observable R1 has already emitted before. And a new emission from the source observable R1 means that the current child observable R2 must be cancelled or unsubscribed and be replaced by a new child observable returned from the function f. There are additional cases for switch map that deals with the termination condition, which adds extra complexity to the RxJS semantics. Based on the semantics, we can have a few ideas for debugging RxJS programs. The first idea is to provide different form of stack traces depends on the execution state of an RxJS program. The second idea is to alert programmers if the subscription enters some unexpected states. The third idea is to check invariants statically or at runtime to provide some assurance of the properties of the program. Normal stack trace of RxJS program may contain too much internal calls of the library to reveal useful information. We can define a more usable representation of the stack trace based on the semantic states of the program. We call that RxJS program has three phases: construction phase, reactive phase, and sequential phase. During the construction phase, the program behaves like any synchronous code with normal stack trace. During the reactive phase, however, the synchronous computation ends. The program reacts to events. If an error occurs, the stack trace should just include the part of the data flow graph that leads to the error. During the sequential phase, synchronous user code is running after reacting to some events. In this case, the stack trace should include both the normal stack trace within the user code, as well as the data flow path that proceeds to the call to the user code. Detailed semantics of the RxJS observables also revealed possible unexpected states of the subscription objects. Some of them are caused by early completion of the sources. For example, the combined observable will not emit anything if one of its sources completes without emitting any value. The combined observable won't complete either until the remaining sources completes. This problem is hard to diagnose since this behavior is not distinguishable from other causes, such as when there's no emission from the source. Thus, it might be useful to generate an alert when a combined observable enters its unexpected state. Similarly, in the concat observable, the first source may complete without emitting anything. As a result, only the events of the second observable source will be emitted. Every observable is supposed to emit true if all event values of its sources satisfy the Boolean function f. However, it also emits true if the source completes without emitting anything. While these are not technically errors, they may be covering up some logical issues in the program. Lastly, in the switch map, if the source observable always emits before the child observable does, then no event will emit either. Come back to our motivation example. We can detect the problem by checking a runtime invariant. where each event source must be uniquely guarded by a catch error observable or by a top-level subscriber. Checking this can be done recursively by following the subscription graph. In the error version of the example, the catch error observable guards two event sources. In the corrected version, the from event observable is guarded by the top-level subscriber, while the from observable is guarded by the catch error observable. As a testbed for the semantics, we have implemented a subset of RxJS. We implement observable using a thread-like abstraction, which we call async-m, which is essentially a promise chain, but it can be cancelled. Each observable is like a thread that emits event to an emitter object, where a subscriber listens for events. To unsubscribe an observable is to cancel the corresponding thread. The top-level subscription to an observable will start the observable thread, while the continuation callback of the subscriber waits for each event to run. The implementation of map observable is very similar, where the events from the source observable is mapped to a function f, and the results are re-emitted. The implementation of switch map is to spawn a new thread to represent a new child observable each time the source emits, while canceling the thread of the previous child observable. Implemented 100 RxJS operators, even though we did not cover all the options. Our implementation provides a subscription graph access to help with debugging. The subscription graph contains very little redundant information, and it helps us to see the internal states of the subscription objects as well as the previous events that has been emitted. We only support the default scheduler so far, but RxJS library also provides schedulers such as asynchronous scheduler that uses the JavaScript event queue for internal events. We can switch to this type of scheduler with very little changes. RxJS also supports ASAP scheduler, which uses the promise queue for internal events, animation frame scheduler, and a queue scheduler that places internal events in a separate queue. One of the challenges for implementing RxJS library turns out to be the precision of timer. For some reason, we are not achieve the same kind of precision for timer as RxJS. In conclusion, the semantics of RxJS may be modeled as a transition of states using a heap and a queue. The subscription graph in the heap is useful for debugging purposes. We can use it to check the runtime invariants. We can check the possible unexpected states in the subscription objects. We can also use it to generate more informative execution trace. There are some remaining challenges. For example, there are over 100 RxJS operators with many options. Modeling them all using rules seems too daunting a task. There might be a better way. Also, events can be emitted as side effects. RxJS library has classes called subjects, which allows user to directly emit events, and such event emission code can exist anywhere in the program, which complicates analysis of the behavior. That's all my talk. Thank you for listening.
So, I have one question. Can you compare your debugger with some other debugging method for reactive programming, such as time traveling or something? Can you hear me? So, can you compare your debugger with some other debugging method for reactive programming, such as time traveling?
We can't hear you. Are you muted on your microphone?
Can you hear me now?
Yeah.
Yes.
Hello?
Yes, hello.
Now we can hear us.
Hello.
Hello?
Can you see my
Your video is going off and you're muted.
We're almost there.
Yeah. Can you hear me now?
Yes.
Okay. So the the closest semantic model, I believe, is with FRtime. If I recall correctly, FRtime also has this operational semantics that describe a reactive, describe a event. Push-based system, FRP system, and I think RxJS is closest to FRtime in terms, at least for the semantic rules that I described using using heap. Is similar in that regard, and it deals with similar issues such as constructing the subscription graph. And then entering different phases from the initialization to event reaction. But FRtime spent quite a bit of mechanisms to deal with glitch. So RxJS does not handle glitches. So in that regard, it simplifies things quite a bit. But on the other hand, RxJS has so many operators, and also it's not as pure. It has it deal with side effects as well as unbounded caching of events. So there's also, other than does not handle glitch, but also it has this potential of memory leak in RxJS. So the number of internal states that RxJS handles is far greater than some of the academic proposal.
Okay, thank you. So, any other questions? No? So let's thank the speaker again.